Welcome back. So here we are with our rank order versus Copulas model. So the first thing we're going to do is we're kind of explain what the model is, how we went about it. And one thing to bear in mind, we're not here to compare the packages on correlation itself or copulas or whatnot. We're just trying to get an understanding of what is a copula. First time I heard about a copula, I thought someone was saying a dirty word to me. So, and I'm sure that I'm not the only one that probably has thought that over the years. The first thing we need to get an understanding of is what's the data we're working with. So we're objectively trying to correlate Series 1 to Series 2. And if we wanted to achieve this, the way we would do it is using either a scatter plot as we saw in our presentation earlier, or you could even use an Excel function called Corel. So just to give a quick example, if we wanted to do this, we would be able to click over here. So equals Corel, this is the function to do Pearson correlation, and then it asks for an array. So in this case, we'll just highlight that. And then we need to highlight the next one. And that will give us Pearson's correlation coefficient, which here is 0.31. Now, what we can see is that this number is very similar, so this is Pearson's, right? Is very similar to our rank order correlation by Spearman. However, if we were to take the number one entry over here in Series 1, and instead of it being 13,000 or thereabouts, we make it 20,000. And then look what happens to the correlation. So it changed a bit over here, and an outlier as much more as being, say, for example, 50,000. Well, look what happens to our correlation with Pearson's, but look what Spearman. So what it does with Spearman is that it kind of, how should I put it, smooths out the outliers, okay? And it is a more stable form of correlation. Now, there are two ways of calculating it. The standard Excel way is that you create a ranking of each data set over here, and you, before we forget, why don't we set it back to what it was? So over here, so 12,966 and 37, and we have our correlation came back. Now, what we did is that we ranked each one of these values in its own list. So we know that this value is the 9th, this one's the 11th, and the highest ranking value is over here, 12,933. So the other aspect of that is that you would then use the same Pearson correlation function and apply that to ranks 1 and 2 instead of the values, and that'll basically give you the exact same thing as a Spearman rank order. That's the way you calculate it within Excel. Vose, on the other hand, has a nifty little function called Vose Spearman, and it helps you calculate that. So if we're looking at the data itself, in order to keep the fitting out of the picture, we have used a ogive, okay, or a custom non-parametric distribution. And the numbers are close enough that that makes it comparable. And over here, so we've calculated what a Spearman's rank order is. Here and without actually pulling it up, what we did manage to do is to fit a copula. So we fitted the copula, and these are the various points. And it generates a U parameter, which is basically a percentile sampling. And it does this, and this is how we obtain a correlated, two distributions are correlated together using the simulate function. And of course, in order to do this fitting, you would have to know what the parameters are. So when you're working with copulas, you're not just working with one parameter, you're working with two. So you're working with the alpha and sometimes can be theta, depends on the copula that you're working with, and then of course the direction. If you do not have these parameters, you cannot use a copula short of trying to approximate what this might be. So in the standard edition, you can try to approximate this, but there is not that fitting capability, though you could model a copula. Now what we're going to do is we're going to simulate, and we're going to compare at first the uncorrelated distribution, see if we're working from an even field, and then we're going to take a same look at the two distributions, but this time with the correlation enabled. So let's look at what this gives. And we're going to use the crystal ball, because crystal ball is the only thing that will run crystal ball. And it also happens that it will, if you run it in normal speed, it can also run ModelRisk assumptions, and I would add at risk and solver as well. So the functions are kind of interchangeable. And let's make sure that the run preferences are set correctly. So the speed is set at normal. And we're going to run this for 5,000 trials. Now this is going to take a little while, so I'm going to talk with you a bit, and then I'm going to pause, and we'll come back when the numbers are generated. Now, as we mentioned earlier, we're not going to, in our next series, we're going to compare things like speed and ease of use on applying copulas and correlation to your spreadsheets. It is worth noting that this is a very important tool in the modeler's toolkit, and it has to be implemented. Otherwise, you could make some bad decisions. You know, if you have just if things are independent, you have very little correlation, you might not notice it. But in some other situations, we've seen correlation shift the mean substantially. So as a general rule, it's very important to implement it. And of course, correlation versus copulas do have certain different performance considerations and use cases. So a lot of that will be covered then as well. So I'm going to pause the recording, and we'll be back to look at how these guys compare. Okay. Now we're done simulating, and we can look at the answers. So as we can see, the general shape of the distributions are the same. Probably the choppiness of it might be a question more to do with the sampling methods that are, that are being used within these objects. So the way they do the math. But for the most part, and I would add another thing, you have to bear in mind the scale, the probability scale. So that kind of highlights a bit the choppiness of this distribution versus the other one. So overall, I would, from visual inspection, we're pretty much dealing with the same thing. The best way to look at this is to pull up an overlay chart where we compare forecasts. So over here, we're going to overlay. So we're going to choose our forecasts, and we are going to take the uncorrelated, and we're going to look at them over here. So what we can see is that for the most part, these two distributions line up pretty well. I would maybe add, from a charting perspective, we could put in a little 3D and some transparency so we can compare this a little better. So by turning on the 3D, we can flip this over and look at the other side and see that they do line up. The tails kind of work out to the same. They sample just a bit. But one of the nice features of looking at an overlay chart is that we can then compare the statistics. And we'll notice that the mean is very close, the median. We weren't able to pick up a mode over here, but that's okay. The standard deviation is a little higher on the uncorrelated, and you can see that the kurtosis is quite similar. Skewness is fairly close as well, and our mean standard error isn't. And of course, if we look at our min and maxes, everything kind of adds up. So if we want to just make sure that we're comparing apples to apples, this would be one way of doing it. We could have maybe have done it another way, but this will definitely suit the purpose. Now what we want to compare is what happens if we pull up the correlated versions of these same distributions and see what happens. So over here, of course, these are the sums of these two distributions, and we can see that, again, for the most part, these two distributions share some commonality. However, what is worth noting probably is here that we have a peak. So another type of overlay chart that we haven't done and that we're going to do is we're going to compare what ModelRisk, because we don't need to, well, we'll do both actually. Create another overlay chart, and this overlay chart will be to compare the copula, the correlation of copula, against something that was not. So MR uncorrelated in MR copula, and here we go. So if we again put on the transparency in the 3D, we can see that is somewhat of a difference here. Whereas you see the tail has been sampled, again, as we saw here, and compared to the uncorrelated, it's got a little more risk here. So we talked about that. And here as well, we have more risk that's pinched in this aspect. So if we enable the rotation, we can get a better look at that from the other end. So this right here is why really the key difference between a copula. And with the crystal ball, we're looking at the same, but we don't have as much going on in the tail. So naturally, this model, when it is correlated, you know, using even Spearmans, there's something going on in the tails, but it's not as pronounced as we would have it with a copula, because we saw the pinching and so on. So to conclude, why would we use a copula? Because we are concerned with the risk in the tails. So who would want to use this? Probably someone in the financial modeling industry, a bank, etc. But not for, and maybe some engineering applications, biology, epidemiology. So thank you very much, and if you have any questions, get in touch at etorque@technologypartners.com. Thanks.